Good. Yes, it is good afternoon. Thank you so much for being here. It's a pleasure to be here. I think you actually just gave my talk, so I may just sit down. So following on from, not that I actually heard the panel, but I did hear the questions for the last session. And that idea of what we do to benefit life. And it's great when somebody asks you to do a Codex talk and they say, literally, you can talk about whatever you like. And we had like a little competition in my team over, exactly what I was going to talk about. And given that the real sort of focus here on the benefit to life and society, the idea of are we alone seemed like a really interesting thing to talk about. So when we think about are we alone, everything the only life that we know in the entire universe right now is on this planet. And even more than that, every body and everything in history that's ever happened has been on this pale blue dot that we call home. And so it seems natural that we would want to know more about the universe around us and, just ask these big, profound questions. As you said in the introduction, we've been searching for exoplanets. We've been searching for planets that orbit neighboring stars, and looking for ones that could be have the ingredients to allow it to support life. Now we have 5,616 confirmed exoplanets as of last month. There are more than 10,000 candidate exoplanets, and that is in about, I think it's 4,312 planetary systems in our galaxy alone. And so it seems crazy, if almost arrogant, to think that we would be the only life in this huge universe. But this question is a very profound question, because when we answer it, it will change us. But I want to sort of, in this talk, kind of go through why we search for life, how we search for life, and then sort of delve into kind of what is life. So why? I mean, why do we search for life? Why do we study the universe? It's for the reasons that we do that are kind of as vast and as varied as the reasons that we explore mountains and we explore deserts and we explore the oceans here on Earth. Ever since the dawn of humanity, people have wanted to explore. They have wanted to know more about the world around them. And that can be, just because we're curious. It can be because we're looking for better resources. And it can also be because we're trying to better life for ourselves here on Earth. And so it seems natural as well that we would then want to search the universe, not just looking for life, but also so we can understand our place in the universe. And as we answer these questions, and obviously as you start answering questions, more and more questions, it's the scientific method, more and more questions are born. And so we want to actually understand our place and understand life here on Earth. Like, how did we form? Why did we form? Where are we going? And how long are we going to last? And this is very, very key to one of NASA's themes, which is the search for life elsewhere. Now, to answer these really big, bold questions, we need big missions and we need bold science. And so we do have a program in the Science Mission Directorate called Astrobiology, and that is really, it sort of encompasses just the kind of the thirst for the search for life, as well as learning more about how life started here on Earth. And I think of it sort of in terms of two thrusts. One is very much studying our own solar system and trying to figure out what life was like before we arrived, or what the world was like before we arrived. And the other, of course, is peering out into millions, billions of light years away to allow us to look at other stellar systems. So we have many missions. We have about 144 missions. I keep saying about. I have exactly 144 missions. I counted. And they're in various stages, from PowerPoint up to maybe 47 years in space with my beloved Voyagers. But some of these missions are really key to explaining our place in the universe. So last year we brought back samples from an ancient asteroid called Bennu. I'm sure many of you watched in awe as that amazing capsule touched down in the Utah desert. We've opened it, we've looked at those samples, and we've already found in those samples traces of water and of carbon. They are the building blocks of life. The reason Bennu, there's two reasons Bennu's really interesting to us. One is it is a very old asteroid. It was around at the time of the Big Bang. So as our solar system was forming, that asteroid was present. So it does allow us to, again, try and sort of figure out what the conditions were like before life started here. We are extremely noisy. As a species. We have polluted, and I mean that in a good way, we have kind of polluted our entire planet. It's very hard to figure out what it was like before we were here. You have to go to the desert, to the outback in Australia to get anything that's remotely like what it might have been like before we arrived. So we can learn about, what that ancient solar system was like. The other thing is, in about 100 years, Bennu will make a very close pass to the Earth. And so, again, as we do planetary defense, we want to be able to make sure that we could do good things and help if that asteroid was indeed going to come very close. We will launch at the end of this year, we'll launch Europa Clipper, which will go out and fly around the Europa moon of Jupiter, flying hopefully through methane plumes that are coming through the surface. The James Webb Telescope has been doing some really amazing images of Europa, and our trajectories we're hoping will go through. And again, find out what's in that sort of, that ocean that we think is beneath the frozen surface of Europa. 2029, we'll launch Dragonfly, which is an octocopter. It's about the size of an SUV, and it will literally hop around the moon Titan, so Saturn's moon Titan. Titan is very interesting. Like the Earth has a carbon cycle, Titan has a methane cycle, so you could almost imagine kind of waterfalls of methane and deep pools of methane on Titan, but carbon rich. So very much we know there's carbon, we know that there's methane there. And again, what was life like before we arrived and got really noisy? We are in the process of trying to bring samples back from Mars. Again, looking down deep in the Martian regolith, what was life like on Mars before there was no life? Was there life? That's a really good question. Was there life? If there was, what was that condition like on Mars before it disappeared? The other thing we do, of course, is use our amazing telescopes. And we look for these exoplanets. And I noted 5,616 exoplanets. So that they are planets that are just, going around stars. We actually try and narrow this down as we look for planets that could be, the easiest thing to do is always look for something that you know. And we're all very comfortable with the Earth because we know it very well. So we want to look for things that are like Earth. So we want to look for a planet that's rocky. It's about the same size as Earth. And we know from our own solar system that massive planets, very unhospitable, highly unlikely that anything ever lived on Jupiter or Saturn. They're big gas giants. So we're looking for a rocky planet that's about the size of the Earth. We look in something called the habitable zone. So we're looking in a region where it's not too hot, not too cold. Oceans could exist. It's not too close, not too far. It's the Goldilocks planet, which is how we think of Earth. The problem is most of the exoplanets that we found that are rocky and about the size of Earth are indeed orbiting around red dwarfs, so stars that are not like our star. We also need to look for the relationship, which is why we study our sun in so much detail. We need to understand our relationship with our sun. It is prone to tantrums and throws off billions of tons of coronal material that can travel at millions of miles an hour to our planet. We call that space weather. It can interrupt our technology. But we have a really good understanding of our relationship with our star. So that's really important as we're looking for stars that could also support life in other stellar systems, understanding what the star is like. So we need to also make sure it's not a massive star that's really prone to like sterilizing superflares, because that would clearly negate anything. Now, you mentioned the very imaginatively named K821b. I don't know, somebody must have spent a long time coming up with that cool name. But that is a planet that was discovered with the James Webb Telescope. And that is an unusual exoplanet. It is about, the radius of that planet is about 2.6 times the radius of Earth, so it's about 5.5 times, 6 times the size of Earth. It's in the right zone. We know that it has an atmosphere. With the James Webb Telescope, it's not just finding exoplanets, but they use something called transit spectroscopy, and so it sort of takes light, spreads it out into a sort of larger than the rainbow spectrum, and we can kind of read that like a barcode. So we can actually do that and then figure out what the molecules and the chemistry is above, in these skies, above these very distant worlds. And so in that atmosphere, we certainly have found carbon dioxide, traces of water, and methane. And so, the ingredients of life. With it being 2.6 times the size of Earth, it means it's kind of it's what we call a sub-Neptune. So it's between the size of Earth and Neptune. We don't have anything like that in our solar system, so we have nothing to really compare it with. So as you can imagine, it is a big debate with people, with astronomers, about, could this really harbor life? We expect, with it being 2.6 times the radius of Earth, though it will have a large mantle, containing some very high pressurized ice, so very much like Neptune, with a very hydrogen-rich atmosphere and possibly an ocean, liquid on the surface. But we don't know that. We also don't know if the ocean could be so hot that nothing could actually live in it, or indeed if it's still liquid water, if it's actually heated and no longer liquid. So there's a lot more work to be done, but it's a really tantalizing look at planets in other stellar systems. And so we continue to do that with the James Webb Telescope. But as we get more and more interested in these types of planets, these types of exoplanets, we actually need much bigger and more capable telescopes. So in a couple of years, we'll launch the Nancy Grace Roman telescope. On that, it has a sort of novel instrument called a coronagraph. Many of you may be familiar with a coronagraph. That's how we look at the sun when we don't have an eclipse. We're able to actually see the corona, and that's how we can forecast space weather. With a stellar coronagraph, we actually want to block out the distant light of a star so we can actually really resolve the planets around it. So the one on the Roman Space Telescope is the sort of demonstration of the technology. Coming right after that, we've just started work on the technology to enable something we're calling the Habitable Worlds Observatory. And the goal of this is to find planets that could sustain life. The goal is to find 25 habitable planets with this mission. The mission builds, as all of our astrophysics missions do, on the missions that have come before. So it is a telescope about the size of the James Webb Telescope. It will use the wavelengths of Hubble, which was the first time we really started to look and find exoplanets and then start to be able to see if they had an atmosphere. Obviously, Webb allows us to kind of look at what's in the atmosphere, but Hubble did a great job of finding that there was an atmosphere. And then we'll fly a coronagraph based. It'll be a next generation of the one on Roman, and that will be habitable worlds. And that is how we really do hope to propel the search for life forward. But I want to kind of finish with just a thought about what do we mean when we talk about life. Do we have a kind of a universally agreed definition of life? The easiest thing to do is to look for what we know, which is life as we know it. But we're much more likely to find life as we don't know it. And I don't mean at this point like a Steven Spiel-esque character that likes to phone home a lot. I mean things like extremophiles, things that are, you can find here on Earth that actually live and thrive in the caustic chemical pools in the Yellowstone National Park. Things like those superheated vents in the ocean, or the totally dry, arid regions in Antarctica. These are strains of life that came from the same beginnings as us, but they branched off billions of years ago. And these are sort of forms of life that literally thrive and are totally happy in environments where nothing else could survive. And so we need to get very comfortable with the idea of life as we don't know it. These could be analogs, these extremophiles could be analogs of what we may find. So as we move forward, I want to finish with my bold prediction. So this is one of my favorite images, by the way. As I was talking about earlier, the merging of art and science, right there. So this is Ru Ofiaki. It was actually the 1-year anniversary image from the James Webb Telescope. This is a stellar nursery. This is where stars are being born. This is about 360 light years away from Earth, so it's actually relatively close. But if you actually look there, you can see like sort of jets coming from the newly born stars. They're sort of crisscrossing the image. They are actually sort of smashing and colliding with local interstellar dust and actually kind of causing the molecular hydrogen to glow. And you can see that in the red here. Some of the stars actually have kind of telltale shadows of circumstellar disks, which actually are, the sign that we have new planet systems actually forming. And so I can't believe that somewhere in that amazing image there isn't life. And so we will continue with our future telescopes, maybe to start looking for signs of photosynthesis on exoplanets, to look for the chemistry, to look for the chemicals and the molecules that could actually support life. If we actually found an intelligent technological system, we would be able to see smog and pollution, which you can actually see from a long way from the Earth. And so, I sort of leave you with the idea that it's not life as we know it, but it really is life as we don't know it. And as we move forward to answer the question, are we alone? It really is a profound question. I said at the beginning, the answer will change us as a civilization. Is life everywhere in the cosmos? Is it rare and really fragile? Or are we truly alone in the universe? Thank you.